We now start looking at the internal state estimation requirements of a battery management system. And we start by looking at the requirement of estimating state of charge. And before we discuss that, we think a little bit about, well, what does the vehicle really need to know? And why does it need to know it? Now, sometimes the vehicle controller will want to know things that it doesn't really need to know, and you supply them anyway. But fundamentally, what is most important? So the vehicle needs to know how much energy is in the battery pack, and the vehicle needs to know how much power is available. And if you haven't spent time making those clear in your mind yet, this is really critical in this context. Energy is a total amount. It's kind of like the total amount of gasoline in your car, your tank. Power is the rate at which you can use energy. So the horsepower of your car, if you have a high horsepower car, means that you can use that energy quickly, which basically means you can accelerate and stuff like that. I need to know both of those quantities. Energy is most important for an EV-like application because energy is like the total amount of gasoline in your tank. It tells me basically how far I can drive. I mean, not specifically. We just talked about range estimation being somewhat different from energy estimation. But that's the idea of what capability do I have presently to do work. Power is most important for things like HEV because hybrid vehicle has a gas engine and the electric motor. It can use the gas engine to drive all day, so it's not a range issue. It's more an issue of how quickly can I take energy out of the battery pack to assist the gas engine to accelerate, or how quickly can I put energy back into the battery pack for regeneration purposes when I do some braking, for example. Those are the extreme cases. In between, I've got extended range electric vehicles and plug-in hybrids, and they both kind of operate in either mode, the hybrid mode or the EV mode, depending on where you are in the operating characteristic. And so I need to know both. They're both important in that case. So, bottom line, the two most important quantities, if I could just nail these, get them right every single time, I would have the best battery management system on the planet. Ideally, we would make a sensor, an electronic device that would sense how much energy is available in the battery pack and how much power is available in the battery pack. No such device exists. I have to compute the energy storage and the power capability from other quantities. If I happen to know all of the states of charge for all of the cells and all of the capacities of all of the cells, that's enough information for me to be able to compute the energy. If I happen to have the states of charge of the cells and the resistances of the cells, that's enough to at least estimate the power capability, although I can do better if I know other things. So in this figure down below, we say, these are what I want. I want energy. I want power. Can't measure them. Got to estimate them. Well, so I've got some calculations that we'll go over in this course on how to do that. I need to know the cell capacities Q, the cell states of charge, the cell resistances. If I know all of those things, I can compute energy and power just as I wish. So great. So let's make a sensor, an electronic device that measures capacity, state of charge, and resistance. Well, sadly, those don't exist either. I can't actually measure them. I have to somehow compute them or estimate them. What can I measure? I can measure voltage, I can measure current, I can measure temperature. So each cell voltage, the stack current, and each cell temperature or some subset thereof. And then I can use algorithms, computational methods, equations, if you will, to convert the primitive things that I know how to measure. We talked about those a couple of sections ago. We convert those measurements into estimates of capacity, state of charge, resistance. And I use those estimates to then produce, finally, energy and power. Those are the most critical outputs. That's the big picture. Now, whenever it comes to producing estimates, there's different ways of estimating things, and there's easy ways and there's hard ways and good ways and poor ways. Usually the poor ways are easy and the good ways are not so easy. So there's trade-offs. The poor methods are simpler to understand, they're simpler to code, they're simpler to validate, but they're not as accurate. So a question to ask before we get too far in this course material, because we're going to spend a lot of time looking at this especially. Once we know how to do this, then we'll look at this, and that's not necessarily as hard, although we'll see there's nuances. So we're going to spend a lot of time looking at how do I estimate the battery state and the capacity and the resistance and so forth. Why bother? Why not just use a simple method and be close rather than being really close? Well, here's an idea. The impact of using a poor method could be this. Suppose I'm driving down the road with my cheap car, and the cheap battery management system is telling the vehicle controller, oh yeah, you've got 30 kilowatts available, no problem. And so when you go to pass the semi-truck in front of you, you floor the accelerator pedal and you pull out to pass the semi-truck, and sure enough, you're drawing 30 kilowatts. And then the poor battery management system says, uh-oh, I was wrong. Did I say 30? I didn't really mean 30. I meant 10. Now what? Well, one thing you could do is you could say, I'm just cutting off all battery power. You can only have 10, you can't have 30, and you have an abrupt correction to the power delivered from the battery when some limit is exceeded because my algorithm did not do the proper job in predicting the power capability. So I'm passing the semi-truck. I think I'm going to make it. I think I'm going to make it. All of a sudden, no power. Uh-oh, now what do I do? I die. That's not good. So the customer dies, and you get sued. That's not good. Or the customer survives, and you get sued. In any case, the customer is never buying your vehicle again, ever, no matter what. And that, you've lost money. So suppose you do something else. So you say, okay, you can have 30 kilowatts, and the guy pulls out to pass the semi-truck, and you realize, oh, I made a mistake. I said you could have 30 kilowatts. I was wrong, but I don't want to just cut off power because that's a safety concern. Instead, I'll honor my prediction, even though I was wrong. I'm going to honor my prediction. I'm going to let you take 30 kilowatts out of this battery pack, which probably can happen. You can probably still do it, but we're going to either overcharge or over-discharge cells. If I'm accelerating, I'm going to over-discharge cells, and that's going to cause damage. And my battery pack will not last as long. It probably won't fail immediately. That would be pretty rare. It'll probably just fail in a matter of a few years rather than the 10 or 15 years that we have designed for, or we are trying to design for. So that means that we're going to have to settle a lot of warranty claims because we've made a warranty on the battery pack for a certain number of years, and we're going to get a lot of people returning their battery packs because the algorithms did not do the proper job of saying how much power was available, and that costs. So the third thing you could do is, okay, I've got a bad algorithm. I know it's going to fail sometimes, but I'm not going to abruptly correct. I want to avoid overcharging and over-discharging, so I just put a lot of margin. I compensate for the uncertainty of the power estimates by over-designing the battery pack, by putting in more cells than I really need. Well, battery cells are expensive, and so your vehicle is going to be more expensive than it needs to be if you do that. So these are the three outcomes I can think of if you have a poor method in your battery management system. Yes, it was simpler for your coder to understand, to implement, and to validate that it's operating the way that you think it should, even if it's not operating correctly. But the less accurate results have real dollars and cents cost. either in dollars or in weight or in volume, and all of those really boil down to a dollar cost of the vehicle. So it's my premise, my soapbox. Can you tell I'm kind of passionate about this? It's my belief that it makes a lot of sense to use the best method that you know how to use, because even if you put some engineering dollars into paying some people to develop good methods and to code good methods and to validate good methods, you're going to save money in the long run because your product is going to work correctly. There's not going to be abrupt corrections. There's not going to be overcharge and overdischarge, and there's not going to be over design of your battery pack. So the customers are happy. Your product is smaller weight, it's smaller volume, and really, when you factor in design plus product, it's going to cost less in dollars because you can get away probably with a much smaller battery pack because you're not over designing it. So that's my soapbox. A major premise is if we invest in a good battery management and control algorithms and electronics capable of implementing the algorithms, by that I mean you're not using an 8-bit microprocessor, you might be using a 16 or 32-bit microprocessor instead, which is still pretty inexpensive, frankly, that we can reduce pack size and we can end up with a net savings. All right, so that's the end of my soapbox. Refreshing our memory, how did we get there? We want to estimate energy and power. To do that, I need to estimate from voltage, current, temperature the capacities, states of charge, and resistances of cells. Thinking a little bit about state of charge here, how might I go about thinking about state of charge of a battery? And I ask you to think a little bit about a battery cell based on what we learned in the previous course in 5710, and from a physics point of view, is that when we charge a cell, lithium is deintercalating from the positive electrode active materials, it's crossing the electrolyte, and it's intercalating into the negative electrode active materials, and discharge does the opposite. So I'm moving lithium, roughly speaking, from the positive to the negative electrode. Okay, well let's focus on one electrode, maybe the negative. And electrochemically, the cell state of charge is related to the average concentration of lithium in the negative electrode solid particles. And we can talk about a stoichiometry, a lithium concentration stoichiometry of a cell, as the average solid concentration divided by the maximum theoretic lithium concentration in the active materials, and that gives us a fraction between 0 and 1. So, theta equals 0 here, and theta equals 1, or 100% right there. Now, usually, always, we operate not between theta equals 0 and 1 for various reasons that include the breakdown of the materials if we do that, but we operate within some window. So there's a little bit of safety margin built in here, so that the thing I call theta 0% is different from theta 0, and theta 100% is different from theta 1. This is simply the stoichiometry, or the concentration ratio, the utilization ratio, in the electrode when the cell is considered to be at 100% state of charge, and this is the ratio when the cell is considered to be at 0% state of charge. That's our operating window. And so you can see the cell, the green one is fully charged, yellow is partially charged, red is low charge, and empty is no charge in the image that I have there. Then I have this gradient here trying to show between full with the black and empty with the white, just to kind of give this overall idea. In any case, the stoichiometry of the cell is intended to remain between those limits, theta 0% and theta 100%. And a cell state of charge is just where am I in this window, in this relative window. And so we compute it as z of k, k being now, it's a time subscript, is the present theta, probably I should call that theta k, minus theta 0% divided by the theta 100% minus theta 0%. So that is how to think about cell state of charge electrochemically. But there's no sensor that I can use to measure this, I'd really need to be able to measure CS average or theta, one of those two things. There's no sensor presently that can do that, although I've talked with some people who are thinking about sensors to do that. Really all we have are measurements of voltage, current, and temperature. Okay. So it's reasonable to wonder if there is some coupling between state of charge and cell voltage. Maybe I can measure a cell voltage and somehow infer state of charge from that. Well, again, asking you to go back and think about a cell electrochemically as we did last course. The cell voltage depends on a number of things. One of them is temperature, because that influences the open circuit potentials of the electrodes. That's kind of a minor variation, but it does depend on that. But moreover, it depends on some internal concentrations in the electrolyte and so forth. That's a fairly minor effect. The most important effect, though, is the electrode particle surface concentrations of lithium, what we called CSE last course, not the average concentrations, which is the CS average here. So if I have a particle and I've been actively using the cell, these core concentration of lithium may be quite different from the surface concentration of lithium, because if I've been charging the cell, I've been pushing lithium into the negative particle, and so the concentration is high at the outside and low at the inside. But then the average concentration is the average over this whole particle, over the whole electrode, really, and that can be very, very different from the surface. So voltage depends on the surface effect, and state of charge is the average effect. And they're not generally the same. And I can at least get close to it if I allow the cell to rest for a very long period of time so that the concentrations become close to the average. But even then, there are some tricks. So changing temperature changes cell voltage, but not concentrations, and so it does not change the state of charge. Resting a cell changes its voltage, but it doesn't change the concentrations, so the average concentrations, that is, so it doesn't change state of charge. History of cell usage, I'm thinking of hysteresis here, changes the steady state surface concentration versus the average concentration. So there's just some tricky things. So in summary, state of charge of a cell changes only due to passage of current, either charging or discharging, due to external circuitry or some internal self-discharge within a cell. So voltage, this current is the primary impactor of state of charge, really the only impactor of state of charge. So voltage is an indirect indicator of state of charge, but it's not a direct measurement of state of charge. Okay, so voltage is particularly troublesome to use as a state of charge estimator element, although any good state of charge algorithm will use voltage as an input, and we'll see that in chapter 3. Well, how about current? State of charge is related to cell current. We saw this last chapter also, that state of charge at some point in time t is state of charge at time 0 minus 1 divided by the total capacity, integrate over time the coulombic efficiency times the current between time 0 and time now. Cell current in this equation is positive on discharge, it's negative on charge. Eta is coulombic efficiency, it's close to 1, but it's less than 1. And Q is the cell capacity, in this case, to get units right, it's in ampere seconds, but we can normalize to ampere hours also. So current, then, is what changes state of charge. And that's a critical thing. I should also mention in passing that this capacity here is the total capacity of a cell. It's not the discharge capacity of the cell. It's not the nominal capacity of the cell. There's a bunch of different capacities. We'll talk about these more in chapter 4. Electrochemically, the total capacity is a count, a measure of the number of locations in the electrode crystal structures between theta 0% and theta 100% that could hold lithium. It's a count in coulombs, all right, how many moles per meter cubed, or how many moles actually per cell can be held, and multiplied by Faraday to get coulombs. So total capacity, a lot of people say capacity varies with temperature. No, it doesn't. Usable capacity does, discharge capacity does, total capacity does not. we'll see that more in chapter 4. So anyway, SOC is related to current. If I simply estimate SOC by integrating current, that's called Coulomb counting. If I use that integral on the previous page, called Coulomb counting, and it seems like the right thing to do. Mathematically, it's the right thing to do. Practically, it's just about the worst thing you can do. And we'll see in chapter 3 that Coulomb counting has some very serious limitations to it. And one final soapbox before leaving this section. The field is pretty new, battery management, and so it's very easy to develop some bad habits, if you will. So people talk about discharge or discharge capacity, or capacity of cells in ways that is not very precise, and it leads to some misunderstanding. And I'm trying to clarify that here in chapter 4. People talk about battery pack state of charge also, and this is also a really poor definition, a poor way of thinking about this. And here's the reason. We talk about cell state of charge, and we have an electrochemical definition of cell state of charge, so we have a physical understanding. There's a real meaning to cell state of charge, no questions. Battery pack state of charge is a different animal, and I use a very trivial example. This will come up several times in this course of an example to show just how silly the idea of pack state of charge really is. You would hope this never happens, but I've got two cells in series here. One cell, the one on the top, as it happens, is at a low state of charge. We'll call it 0%. This has a 0% state of charge, and this one has a 100% state of charge. And someone says, okay, here's the configuration of the battery pack. It's got two cells. These are the individual states of charge of the cells. Please tell me, what is the pack state of charge? And there's three ways I can think of that we could consider to compute this. One is take the minimum of the two. Because we're thinking in our minds that the state of charge is telling me about how much I can discharge the battery pack. So I could say 0%, because I can't discharge. If I pull any current out of this battery pack, this guy here is going to become undercharged, and that's bad. So I could say, well, it's a 0% state of charge battery pack, if I'm thinking that way. But that doesn't make any sense, because if you tell me my battery pack is at 0% state of charge, I say, oh, I need to plug it in. I need to charge it right now. But I can't charge it. If I put any charge into this battery pack, this cell here is going to become overcharged. So 0% is not the right answer, I don't believe. So we could say, should we call it 100% then, because we can't charge? Well, surely we can't charge, but we can't discharge either. Should we call it the average? Should we call it 50%? Well, that's almost the worst, because 50% leads me to believe that I can both charge and discharge, and in fact I can do neither in this case. So it's my premise, and I'll argue this very strongly, that the term pack state of charge is not well defined. It's ill-defined, moreover, and should really never be used. There will be one place in these course notes where we will define something called the pack average state of charge, which is this calculation, and this calculation can have use, but this calculation is combined in that setting with knowledge of all the individual states of charge as well, so it's not just that calculation by itself. So I will never use the term pack state of charge, I hope. I don't mean to. I don't believe it makes sense. One thing, this example, I mean, it's a trivial example. It's almost impossible to get a battery pack into this situation. It is actually possible, but it's very hard to get a battery pack into this situation. It points out the need for cell balancing, and cell balancing has to do with individually manipulating the levels of charge in the different cells. So I'd like to, ideally, move half of this charge into that cell, and in that case they would both be at 50% state of charge, and then I could I could both charge the pack and discharge the pack. It would be very useful. Right now, that battery pack is not useful because I can't do anything with it. So I do need to look at cell balancing, and we'll do that in Chapter 5. So I should never get in this configuration, but I can get in this configuration without balancing. So that leads me to step back and ask you to consider, why would someone want to even know the pack state of charge? If they came out of a background in portable electronics where you have single cell applications, the idea of state of charge lets you know, how long can my phone run before I need to plug it in again. That's where the pack state of charge idea came from. It came from single cell applications applied to a multi-cell battery pack. It's like, well, wait a minute. State of charge was really not even what you wanted back then. There's two reasons why you might want to know state of charge. One of them is fuel gauge. Fuel gauge tells me how long can this application run before I don't have any more energy left. Energy. The real issue is battery pack energy. For this battery pack here, I can compute for you how much energy is available, and the answer is 0. And we'll look at that later on. But there's 0 energy available because this cell is completely discharged. Doesn't mean that the state of charge of all the cells is 0. It just means that I can't get any more energy out. So for fuel gauge purposes, state of charge was never the thing you wanted to know anyway. Energy was always the thing you wanted to know. How much energy is available in the battery pack? Now, it turns out for a single cell, energy and state of charge are almost directly proportional to each other, so that's probably why people use state of charge, but energy is fundamentally what you want to know. The other reason you might want to know something called battery pack SOC is if you are operating a hybrid vehicle and you want to maintain the battery pack at roughly 50% SOC, whatever that means for you. Because you want to you have a hybrid vehicle, so your gas engine is going to take all the major load anyway, the average load. You want to leave some headroom in your battery pack to accept regeneration at any point in time, or to be able to do some discharge at any point in time. So you want all of your cells to be roughly half charged in a HEV battery pack. So average SOC might work for this. I would not call it pack SOC. I might call it pack average SOC. This here definition might work, but it would really only work well as long as you are also balancing all of the cells on your battery pack pretty well at the same time. And of course, in implementations, people do that. They balance very well, but I still get upset when they talk about pack SOC. We'll look at this more in Chapter 3, where we look at state of charge estimation of battery cells. But now we're going to move on and go into our next topic, where we look at the energy and power estimation, which fundamentally, remember, are the two things that a battery pack really needs to produce for its application. If I know all the states of charge of all the cells, how can I use that to tell the application how much energy is in the pack and how much power the pack can deliver?